Ever seen an AI crush humans at chess or master Go effortlessly? Reinforcement learning makes it happen. But forget the complicated jargon. We are breaking it down into everyday terms, like choosing your favorite coffee shop each morning. Easy, clear, and surprisingly fun. Welcome to AI Club Pro, where we make AI concepts feel like everyday ideas. Reinforcement learning is a technique that lets computers learn and adapt based on experiences. And it's used in many applications, such as training large language models like ChatGPT or Gemini, or help computers become better at playing games like AlphaGo or checkers or chess by themselves. This concept itself comes from game theory with a fair amount of jargon like Q value, agent, reward, policy, etc. In this video, we'll break it down for you in simple words that will help you grasp what it is. You'll be able to decide when it is a good idea to use it. Let's start with a simple example. Let's say that we are going to use reinforcement learning to decide between two coffee shops, Java Haven and Brew Central each morning. Let's start with the assumption that you have never visited either of these places and your goal is to find out which one consistently offers a satisfying cup of coffee. Initially, you have no preference, so you might randomly choose either of the shops. Here's how reinforcement learning can help. Reinforcement learning lets computers, or in this example, you, learn from experiences and adapt decisions accordingly. Rather than relying on explicit instructions, you learn by exploring and receiving feedback. In this case, your coffee is satisfying or disappointing. Let's break down the process clearly. So you start with equal probability of choosing either of the coffee shops. Each morning, you randomly pick a coffee shop based on these probabilities. After drinking your coffee, you rate your experience. Let's say a satisfying coffee gives you a reward of +1, while a disappointing coffee gives you a negative reward. The idea here is that you repeat this process many times, and over time, you learn more about the coffee quality at the two shops. It's not necessary that each visit to the shop yields same satisfaction. It may differ based on factors like the barista, the coffee beans used, or even your mood. Intuitively, humans naturally learn this way without consciously thinking about it. However, creating mathematical equations to model this learning process for a computer involves a fair amount of jargon. Let's clearly define each technical term related to this scenario. Keep in mind that real-world scenarios are far more complex, and we'll later discuss how this simple example of choosing between two coffee shops scales to larger and more complex problems. In technical terms, the agent is you here, who's deciding between two coffee shops. The two coffee shops you interact with constitute the environment. The goal of reinforcement learning is for the agent to discover an optimal policy, which is a strategy to select actions that maximize long-term rewards. In this simplified example, the policy is assigning probability values for visiting Java Haven or Brew Central. Imagine dividing a number line into two parts. You pick a random number between 0 and 1, and depending on where it lands, you choose the corresponding cafe. The state in this scenario is simply your decision making scenario each morning. It's the same state each morning because nothing else changes. The action is choosing either Java Haven or Brew Central. The reward is the satisfaction rating that you're going to give the coffee, which can be a positive one or a negative one. The environment transitions between the same stage each morning because each morning presents the same decision. Therefore, in this extremely simplified example, there's only one state, your morning decision situation, and two possible actions, choosing either Java Haven or Brew Central. Mathematically, we define something called a Q value, which estimates how good a particular action, which is choosing a coffee shop here, based on your experience, would lead to satisfaction. So there's only one state and two actions, so there are a total of three Q values. You can initialize these Q values randomly and then update them based on your experiences at each coffee shop. The rate at which you update the Q values based on your experiences is controlled by a parameter called the learning rate, which is often represented as alpha. This is similar to how machine learning models learn from data. If you're unsure about how AI models learn, please check out our video on what is an AI model. Let's illustrate reinforcement learning with a concrete example. Initially, the probability of both Java Haven and Brew Central is equal to 0.5. The Q values can be initialized to 0 as well, since we know nothing about what to expect. Let's assign 0.1 to the learning rate. On the first day, let's say we randomly select Java Haven and the coffee is disappointing. We'll assign it a reward of -1 and update the Q value for Java Haven to be -0.1. And on the second day, let's say we randomly pick Brew Central and loved the coffee there. We'll receive a reward of +1 and update the corresponding Q value to be 0.1. Typically, you'll use these Q values to modify your policy, increasing the probability of selecting the shop with a higher Q value. Initially, your policy was that the probability of both Java Haven and Brew Central is equal to 0.5. Now, after your two visits, the updated Q values are -0.1 for Java Haven and +0.1 for Brew Central. Based on these updated Q values, you adjust your policy slightly in favor of Brew Central. For example, probability of Java Haven is 0.45 and probability of Brew Central is 0.55. Note that this is based on just one experience. There is nuance in how you update the Q values and the probabilities associated with the policy, which we have kind of skipped over. Now let's introduce additional complexity by considering two different states. State 1, you wake up craving strong coffee, and state 2, you wake up craving milder chocolatey coffee. Now your Q values must account for both your states, which is your craving type, and then your action, which is the choice of the coffee shop. Now you have 4 possible Q values corresponding to the craving being strong or not and the Java Haven or Brew Central. So these are your states and the corresponding actions. So it's a combination of these two things. Initially, all these Q values might start at 0. You now have two distinct sets of probabilities. A policy when craving a strong coffee and a policy when craving a milder chocolatey coffee. Suppose on the first day you wake up craving strong coffee and visit Java Haven and find it disappointing, you give it a -1 reward. Let's say the next day you wake up craving strong coffee again, but this time visit Brew Central and find it very satisfying, then you give it a positive reward. And based on this, you're going to update your Q values. Now the reinforcement learning process becomes slightly more complicated because you maintain separate Q values and policies depending on your current craving. Typically, you'll continue to repeat this process over many days, accumulating experiences and continuously updating your Q values and policies. This allows you to better satisfy your specific daily craving over time. To appreciate how quickly complexity can scale, consider applying reinforcement learning to playing a game of chess. Here, each unique arrangement of pieces on the board represents a distinct state. And because chess has an astronomical number of possibilities in terms of board configurations, the number of states is immense. Additionally, each state can have so many potential actions, which is potential moves that you could make. So unlike a simple coffee example with just 2 actions and a few states, Chess involves billions of states and actions. This massive scale requires sophisticated methods like function approximation in case of neural networks to effectively estimate and update the Q values and policies. In training a deep learning or a machine learning model for such a scenario, states and actions are predefined, but no explicit labels exist to guide the model. Instead, the model updates its internal parameters and weights based on experiences. After taking an action, the model receives feedback in the form of rewards at the end of an episode or sequence of actions. It uses these rewards to adjust its weights, thereby improving its ability to predict actions that yield higher rewards in similar future scenarios. This is achieved through methods such as temporal difference learning, which incrementally update the predictions using the difference between expected reward and the actual outcome. Over time, accumulating many experiences allows the models to develop an effective policy for selecting optimal policy. Reinforcement learning, though rooted in seemingly complex mathematical jargon, essentially mirrors the intuitive way that humans learn from daily experiences. By continuously updating based on feedback, it empowers the computers to make sophisticated decisions in vastly complex environments. So, next time you're deciding between two coffee shops or admiring an AI's impressive chess moves, remember you're witnessing reinforcement learning at its simplest and at its most powerful. Thanks for joining us at AI Club Pro. Hit that subscribe button for more eye opening AI insights. Stay curious and keep exploring.